Good morning. The topic of my presentation for the day is on regenerative endodontics. Endodontics has traditionally focused on treating pulp diseases and trauma by removing infection and preserving the remaining tooth structure. Root canal therapy and epixification, while effective at controlling infection and preserving the teeth, results in loss of tooth's natural biological functions, leaving it in a non-vital state. Teeth treated with these conventional approaches lack the sensory, immune, and the regenerative functions inherent to vital pulp tissue. Over time, this loss of vitality can increase susceptibility to fractures and structural failures, as non-vital teeth often become brittle due to lack of blood flow and cellular activity. Regenerative endodontics has emerged as a groundbreaking field that shifts the focus from merely treating or preserving the tooth to actively regenerating the damaged or the necrotic pulp tissue. Regenerative endodontics is deeply rooted in the principles of tissue engineering, an interdisciplinary field that combines cell biology, biomaterials, and molecular biology to develop biological replacements for the damaged tissues. The foundation of regenerative endodontics rests on tissue engineering triad that consists of three essential components, namely the stem cells, scaffolds, and the signaling molecules. Each element of this triad plays a unique role in promoting the formation of living pulp-dentin complex. Stem cells serve as a cellular foundation for tissue formation, possessing the ability to differentiate into odontoblasts-like cells, essential for the regeneration of dentin and pulp tissues. Scaffolds provide the structural framework that supports cellular growth and organization, while signaling molecules guide cell differentiation, tissue maturation, and vascularization. Together, these components aim to create a biological environment within the root canal that supports the regeneration of the pulp tissues and enhances the tooth's long-term resilience. Historically, the idea of regenerating dental tissues has been explored for several decades, but it was only in the early 2000s that significant progress began to materialize. Initial research demonstrated that stem cells derived from dental pulp and the apical papilla possess regenerative potential and are capable of differentiating into odontoblasts-like cells under the correct conditions. These discoveries have since spurred extensive research into the use of dental stem cells for pulp-dentin complex regeneration. Multiple stem cell sources such as the dental pulp stem cells from the apical papilla, and dental follicular progenitor cells have shown the capacity to generate key cellular components needed to reconstruct the pulp-dentin complex. These findings have opened new avenues for regenerative treatments that aim to re-establish a biologically active pulp tissue, which is integral to the tooth's long-term health and functionality. Regenerative endodontic therapy is currently applied primarily in cases of immature permanent teeth with necrotic pulp, where traditional treatments like epixification or pulpectomy fail to promote continued root development and can lead to a structurally weakened teeth. In contrast, regenerative endodontics can stimulate cellular activity that encourages root maturation and dentin formation, significantly enhancing the tooth's structural integrity. Effective disinfection is crucial to preventing reinfection and to ensure the success of regenerative procedures. Though harsh disinfection agents can compromise the survival of stem cells and thus the overall regenerative outcome. The triple antibiotic paste is widely used due to its broad-spectrum antimicrobial effects, although it can also negatively impact the stem cell viability. Optimizing these protocols to balance disinfection and biocompatibility remains a focus of ongoing research. Recent advancements in regenerative endodontics show promising directions in gene therapy, advanced scaffold designs, and cell-free regenerative approaches. Gene therapy particularly holds the potential for more precise control over cellular behavior by enabling targeted delivery of growth factors to the pulp-dentin complex. Gene-modified cells can express signaling molecules essential for directing differentiation and tissue formation, although its application in endodontics is still largely experimental. Innovations in 3D printing technology allow for the development of customized scaffolds that better enhance the overall viability.